Okay. Last video we talked about the basic four gas laws. We're going to talk about a combined gas law. So the combined gas law is different than the other laws. We still deal with pressure, volume, temperature, and moles. But before, what we were doing is we were holding two of them constant and changing the others. And we're not going to do that this time. Now we're going to be able to look at all of them at the same time. So really what we're doing is this is Boyle's law, and then I'm going to take Charles' law. This is Charles' law. I'm going to multiply those together, and then this is Gay-Lussac law, and then I'm going to multiply that together. And what you end up with is P1 V1 T1 squared equals P2 V2 T2 squared. So you take the square root of the whole thing, and you end up with P1 V1 T1 equals P2 V2 T2. Generally, it's done like this because people don't necessarily change the amount of gas, but this can also be, you can also add N1 and N2, which is moles. So this is the full combined gas law. And so let's go ahead and go with a problem. I'm going to use a problem here. So, you know what, maybe I should just make one up. Let's see. I'll make one up because then you have this one and the one I'm making up. So let's go with this. So let's open that. And I'm going to actually grab one. That's a better idea. So let me grab this. Open up this. And go to worksheets. And we'll go to gas laws. Okay, so under worksheets, there's two really good worksheets for gas laws. One of them is called Gas Law Problems 1 through 27, and then there's Gas Laws 1 through 27 with answers. And then there's another one that says Gas Law Problems 154, 1 through 154. So if you really want to get into this, you can do 154 problems if you want. So I'm going to scroll down until I get to the combined gas law. All right, so then I'm just going to grab this guy right here. Oops, there aren't answers written down for this one. Copy. Then I'll go back over to here and I'll paste that in there. Control V. Okay. All right, so we've got lots of stuff here. We've got a volume. So these are the things we're given. We have this volume. We have this temperature, and we have this pressure, and we have a new temperature, and we have a new pressure. And so the first thing I want you to focus on is, what are you looking for? And so in this case, it's asking me what the volume is. So your answer needs to have a volume unit in it. Let's knock out the 273. So that's 250 K. And 273, so that's 500 K. Oh, that's right, they made this one easy. All right, so I'm going to set up a railroad track that will allow us to do this problem in a way that gives us the volume unit. So I'm going to go ahead and start off with 800 milliliters. So when I'm finished, 800 milliliters, the answer is going to be in milliliters. Great. All right, so now what I'm going to do is I'm going to compare the two things that we have. So we started at 250K and we went to 500K. So now I want you to think, what would happen to a gas that was heated? What would happen to its size? So what would happen to a balloon that got heated up? It would get bigger. I mean, that is the whole deal with hot air balloons. So that would mean I need a number that's larger than 800 milliliters. So I'm going to put 500K in the top and 250K in the denominator. That way I can cancel out the K's and this number will get bigger. All right. So I'm going to do the same thing with my pressure. So the pressure was 300 torr and now the pressure is 600 torr. Okay. So I'm crushing it. And so that's going to make this thing smaller. So I'm going to need to make the 800 a smaller number. So here's 300 torr in the numerator, and here's 600 torr in the denominator. And that way I can get the torr values to cancel out. And then I just do the math, and this one's super easy. because one's 2 and the other one's a half. So you end up with 800 milliliters. So if you did this example, you end with the same thing that you started with. All right, let's go ahead and do one more. Copy. Okay, so we're starting with 2 atmospheres. Oh no, what is the volume of this gas at 2 atmospheres and at 200 K when the original, it initially was 300, 250, and 400. Okay, so I want to know, again, I'm looking for the volume. I want to know what this volume is. So I need a volume unit. The only one I have is 300 liters. All right. So I'm going to take my atmospheres and set them up so they cancel out. And my kelvins, I'm going to set them up so they cancel out. So I was at 400 and I cooled to 200. So that's going to make me smaller. So I'm going to put 200 K up here and 400 K down here. And my pressure was 0.25 atmospheres, and now it's 2 atmospheres. Okay, so that means it's getting crushed, so it's going to get smaller again. So I'll put 2 in the denominator and 0.25 in the numerator. Okay, so we'll definitely get a different value this time. So 300 times 0.25 times, and I end up with 18.75 milliliters. Looks like we have 3 sig figs, 3 sig fig, 3 sig. So, all right, this is going to be 18.8 milliliters for my answer. And that's how you do these problems. I don't worry about the equation. I just know what I'm looking for. And then I set up the problem. So the things that are happening to the gas, I make changes that make sense. So in this case, I was at 400 degrees and now I'm at 200 degrees. So I must get smaller as a gas because my particles cooled. So they're not hitting the walls of the container as hard. All right, let's go ahead and move on. So those are gas laws. There's another example here for you. All right, so the next thing we're going to talk about is the ideal gas law. And so if we were in class, I'd be asking you questions how this one looks different. And so there's two things about this gas law that are different. One, there's no before and after. This is what the pressure, volume, temperature, and moles are now, not after we've done changes. And the other part is there's a constant. This is a numerical value, and this is the constant that you're always going to get. So what they did is they took 1 mole of gas at standard temperature and pressure. So standard temperature and pressure, STP, that temperature is 0 degrees Celsius, and the pressure is 1 atm. Okay, so when they did this, they have the temperature, they had the pressure, and then they used a value of 22.414 liters, and then they solve for R. So R is going to be equal to PVNT when P is 1 atm, V is 22.414 liters, N is 1 mole, and temperature is 273 K. And what happens is you end up with a number, and that number is number is this 0.08206 liter atmospheres, those are in the numerator, and moles and Kelvin, those are in the denominator. That's it. So you will get this every time. And so when you say this out loud, you're going to say liter atmospheres per mole Kelvin. There's another version of it with joules. So joules per mole Kelvin. If you multiply liters and atmospheres, that equals joules. And so this is just a different way to do it. Not a big deal. If you need to use it, you've got another one. Okay, so I'm going to go ahead and go back to that that worksheet. And let's find ourselves an ideal gas law problem. Okay. There we go. We'll just grab this first one here. Copy. Go over here. Scroll down. All right. So, how are we going to get an answer with moles in it when there's no moles in the problem? So, I look at this question and I'm like, okay, so I need a mole answer. And what I have are milliliters, degrees C, and millimeters of mercury. So first, let's knock this out: 273, 294, just to get that done. Okay, so when you see a problem like this, there's no way to calculate moles from the given information. So this must be an ideal gas law problem. The other reason I know it's an ideal gas law problem is because there's no before and after. There's only one volume, only one temperature, and only one pressure. There isn't an after pressure. So that means if this is an ideal gas law problem, I get to use R, which is 0.08206 liter atmospheres per mole Kelvin. So there's a mole in that unit. That's fantastic. All right, I got a mole in that unit. I am going to take this value and I'm going to write 1 divided by 0.08206 liter atmospheres mole Kelvin. I did that because I needed mole in the numerator for my answer. Is that okay? Yeah, it's okay to write this upside down. 12 inches is equivalent to 1 foot, and 1 foot is equivalent to 12 inches. It doesn't matter how you write them because the numerator and the denominator are equal to each other. So they can both be, either one can be on top, either one can be on the bottom. They just have to be opposite of each other. All right, so I just need to cancel out the units that are left. So I'll put 294 Kelvin here. And so that way I can cancel out my Ks. I can put, well, I got to do some unit conversions here. That's fine. I'm going to put 890 milliliters up here. And then I'm going to write 1,000 milliliters is 1 liter. And then I can cancel out milliliters and liters. And then I can do another conversion. So I need to cancel the pressure unit out. So all right, 750 millimeters of mercury up here, but I can't cancel those out directly unless I write 760 millimeters of mercury is 1 liter. And this is on that table of all the different gas laws, the equivalent of, I don't know why I wrote liters. Sorry about that. That's supposed to be, I think, race. That's supposed to be ATMs. 1 ATM is equal to 760 millimeters of mercury. It's on that, I think it's the 3rd page of the notes. And so then I can go ahead and cancel out my ATMs. And the only unit that hasn't been canceled is moles. So then I can just go ahead and knock out this problem. Math, 890 times 750 divided by 760 divided by 1,000 divided by 294 divided by 0.08206 equals. And so I got 0.03, how many sig figs we have? 3 sig figs? 364 moles. There's my answer. That's it. So with these ideal gas law problems, I always start with the number of moles, or I always start with the R value so I can get the unit that I need. That's just the way they work. The only way these things can be a little bit different, we'll do one more. Let me grab. All right, this is a good one. All righty. Okay, so I am looking for a volume, and I have standard temperature and pressure, so that's 273 K, which is 0 Celsius, and 1 ATM. How am I going to get volume? Well, I've got moles, K, and ATM, so this is an ideal gas law problem. Okay. And so same thing, I'm gonna write it upside down, 1 mole. Okay. 0.082206 liter atmospheres. And then I'll go ahead and write 273K here. I'll go ahead and write 1 ATM here. All right. Oh, darn it. We were looking for volume. I messed that whole thing up. Not bad. Let me start over. So we'll go ahead and write 0.08206 liter atmospheres mole Kelvin. There we go. Start over. So 273K, and that way I can get the K's to cancel. And then 1.27 mole. So I can get the moles to cancel out. And then 1 ATM. So the ATMs will cancel out. Okay. And the only unit I've got left is liters. So 0.08206 times 273 times 1.27 divided by, well, that's it, divided by 1. All right, so this is 28.451. I've got 3 sig figs, so 28.5 liters. Okay. That's actually not the problem I wanted to do, but whatever. Let me grab another one. This is actually the one that I wanted. Copy. Okay, so I want to know volume. Okay, great. I have grams. That's not helpful. I have atmospheres and degrees C. So 273, 1, 2, no, not 2, 9. Okay. Yeah, 291K. So I don't have a volume unit. So this is an ideal gas law problem. So I need a volume unit. That's fine. 0.08206 liter atmospheres moles Kelvin. Okay, so now I got my liter in the numerator. That's good. I'm going to go ahead and start knocking stuff out here. 291. Actually, I didn't want to do that. 291K, and then we can cancel out the K's. Good. And then I can cancel out the ATMs with 3.12 ATM, and then ATMs are gone. All right, so how am I going to get rid of that mole unit? Well, I was given 2 things, 32 grams, and I was given the gas type. Couldn't do this problem if I wasn't given the gas type. So I'm going to go ahead and figure out what the molar mass of that is. So 14.0067 plus 15.9994 times 2 equals, and so my molar mass here is 46.0055 grams per mole. All right, now I got our grams per mole. Okay, so I'm going to go ahead and write 32 grams of NO2. I can't cancel those out directly, but now what I can do is write 46.0055 grams of NO2 is 1 mole of NO2. And now that I've got moles in the numerator, moles in the denominator cancel out. Grams in the numerator, grams in the denominator cancel out. So with this problem, you can be given grams as long as you're given the type of gas you're talking about, or the actual formula of the gas. 0.08206 times 291 times 32 divided by the 46 number, and then divided by 3.12, and I get 5 point, what do you have, 3 sig figs? Yeah, 5.23 liters. All right, so those are the different types of ideal gas law problems you could possibly see. Okay, so let's go ahead and move on. So the next one is Dalton's law of partial pressures. This one is a really kind of like, yeah, of course that's the way it is. In the same way that Avogadro's was, if I put more gas in, the balloon gets bigger. So same situation here. Except we're talking about multiple gases and we're wondering how much pressure is being applied by multiple gases. Okay, so let's say that I've got some gas, not that kind of gas. All right, so I've got, I don't know, 1 mole of helium. Okay, and let's say that 1 mole of helium has a pressure of 3 atmospheres, given all the other conditions. That's fine. What happens if I double it to 2 moles of helium? This is, if everything else stays the same, then my pressure is going to switch to 3 atms. Why? Pressure is dependent upon impacts. That's the nature of gases. So if I double the number of particles, that means I'm doubling the number of impacts. So that means I'm doubling the pressure. That's how it works. So Dalton's law of partial pressures is all about what portion of the gas is helium, what portion of the gas is carbon dioxide, what portion of the gas is oxygen. In our atmosphere, if our atmosphere is 1 atm, then I would say 70 or 0.79 atm is due to N2, and 0.20 atm is due to O2, and 0.01 atm is everything else. And by everything else, I mean water vapor, carbon dioxide, carbon monoxide, any pollutants that might be in the atmosphere, argon gas, helium, doesn't really matter, anything else. How do I know this? Well, I know 79% of the atmosphere is nitrogen and 20% of the atmosphere is oxygen, and all the rest of the stuff, that 0.01 is all the rest of the gases combined. Okay, so how would we use this? So if I've got partial pressures, if I know that the oxygen pressure is 2 atmospheres and the CO2's pressure is 3 atmospheres and the helium's pressure is 4 atmospheres, then the total pressure is 9 atmospheres. All right, that's fine, whatever. You could have put oxygen in the container until it said 2 atmospheres, and then added CO2 to the container until it said 3 atmospheres, and then added helium to the container. Sorry, not 3 atmospheres, but 5 atmospheres, and then added helium to the container until it said 9 atmospheres, and then you would know. My question is, why? And so really what we have here is the oxygen is 2/9 of the pressure. The CO2 is 3/9 of the pressure, and the helium is 4/9 of the pressure. So this is my pressure fraction. Okay, well, why are those pressure fractions what they are? And the reason is because 2/9 of total particles, I can't spell, are O2, and 3/9 of total gas particles are CO2, and 4/9 of total particles are helium. So Dalton's law of partial pressures is just about what pressure is felt for each of the gases, and that's all about how many of them there are. So if there's a higher pressure due to helium, like there is in this case, then there's more helium. How much more helium is there than oxygen? There's twice as much, because the pressure is twice as much. How much more pressure, how much more gas of CO2 is there than the oxygen? 50% more. So if there's 1 mole of CO2 or of O2, then there's 1.5 moles of CO2. That's just how it works. So you You can figure out what the pressures are based off of the amount of gases that are there, and vice versa. You know what the pressures of the individual gases are, then you know how many of each of the particles there are. And that's Dalton's law of partial pressures. Okay, so next one is called Graham's law. Graham's law is the only equation of the gas laws that I actually use. And that's because there's a square root in it. And I can't get rid of the square root when I'm doing railroad track stuff. So we'll actually use this equation. Okay, so Graham's law is about the speed of gases in the same container. I've got two gases in the same container. What are their relative speeds? How fast is one moving relative to the other one? You might say, well, they're in the same container, they're moving at the same speed, but that is not the case. Can you imagine a time when a dump truck and a VW Bug have the same amount of energy? So maybe the dump truck is moving 5 miles an hour and the VW Bug is moving 70 miles an hour. Then they'd have the same amount of energy. So temperature is about kinetic energy. So the temperature, the average kinetic energy is equivalent to the temperature of the object. The temperature goes up, the kinetic energy goes up because the speed of the particle goes up. And kinetic energy is 1/2 mv squared. You ever wonder why you're supposed to slow down when you go into a school zone? I mean, it's obvious you don't want to run over a kid, but what does speed have to do with it? How does your car stop itself? You say, oh, well, it's the brakes. Okay, but how do the brakes stop the car? Let me try to pull up. I'm going to pause this and find a picture. Found it. This is a picture of a vehicle that's driving in the 24-hour Le Mans race. So this is a race. If you've seen Ford versus Ferrari, then you know what I'm talking about. But this is a race that happens in Le Mans, this little city. And it's you have to get in the car and drive it for 24 hours. You and one other driver swap off. This is so since they have to drive at night, this is why we're using this photo. What is happening to this car? It is braking into the turn. So what is happening with this car? How's it slowing down? The car's kinetic energy, the car's actual motion is being turned into heat. It's being dissipated as heat. So those brakes are hot and they're dissipating the heat of that vehicle. So they're turning the motion of the car into just excess heat and then just wasting it away. So this car has like super fat, strong brakes, like the brakes on my truck, even though that car probably weighs 1/4 of what my truck weighs. Or a dump truck's brakes are huge. These are discs that have little pads that grab each side, squeeze each side, and transfer heat based off of friction. So literally friction stops you. The most important part of your car are the brakes. Doesn't matter, and none of the rest of it matters if the brakes don't work. So when you slow your car down, you're slowing your car down by turning your motion into heat. All right, great. Why do I slow down inside of a school zone? Is because as I slow down, the amount of heat that I need to dissipate is reduced. So what they've done is, depending on what the what school zone you're in, they reduce it so your car is able to stop in one single car length. Why? I lived across the street from a grade school, and what would happen is you would have these cars parked on the side of the road and somebody else driving their car, and then a little kid would squirt out in between the two cars to get to his mom's car on the other side of the road, dad's car on the other side of the road. So what they did is the speed that you slow down to allows you to stop in one car length. So this person can't see that kid until they're here. So if you slow down to the speed of the school zone, you will be able to stop in a single car length, as long as your brakes are working. And it's a horrible ticket. Like, just slow down in the school zone. The ticket is in Oregon now is over $1,500, and you have to go to driving school if you get that ticket. And you rest assured that those cops hang out there because they're trying to protect those kids. Okay, so what does this have to do with gas laws? And what it has to do with is two gases in the same container will be at the same temperature. So that means their kinetic energies are the same. Well, how can helium have the same kinetic energy as, say, argon? When helium's molar mass is about 4 grams per mole, and argon's molar mass 40? Yeah, about 40 grams per mole. So how do they have the same kinetic energy? Well, they're at the same temperature, so I know they have the same kinetic energy, but since one is 10 times heavier, more massive, it must be moving slower. So in the same analogy of the VW Bug and the dump truck having the same amount of energy, I have to slow it down. So this one is moving slow, and this one is moving faster. So they have the same amount of kinetic energy. So Graham's law deals with this. Okay, how is this useful? Well, you want to know how fast the gas is going. If you want to sell something, the most profitable job for a chemist is in personal care, in like face creams and makeup and all that kind of stuff. And one very profitable section would be perfume. So what makes a perfume good? Well, there's obviously it has to smell good. Okay, smell good. It has to last a long time. Those are the two things, really. And maybe name recognition, whatever. But really, the things that make a perfume good are they smell good and they last a long time. Okay, so let's set aside the smell good thing and let's talk about the last long time. How does something last? How does a perfume last a long time? How does a deodorant last a long time? So the way that a deodorant lasts a long time is it's really big, which makes it really slow. And so the other good part about that is if you put a high quality perfume on, you'll have a little aura around you of scent, and it won't go outside of your personal space. The only way somebody else is going to smell the cologne or the perfume you're smelling is if you hug them. You get them in close, which is awesome because I've definitely had some guys walk into class and smell like they actually did the Axe commercial and sprayed double-fisted 2 cans of Axe spray all over their bodies. That don't want that. Why? Because Axe is cheap. Axe is very volatile. Axe is made of very small substances, and they leave your body very quickly. So you come into the room, and by the end of class, you won't have that much spray on you because the whole class has been subjected to your body spray. So please don't do that. Nobody likes that. It's terrible. Don't watch those commercials and say, hey, I should do that. So how are we going to do this? Well, this is the equation, 1/2 mv squared. And if I know that these two things are equal to each other, I can say, I can get rid of the half because the half will be on both sides. And then I'll just have mass times velocity squared, mass times velocity squared. So one other thing with this, velocity is way more important. So if I double the mass of a vehicle, it will have double the kinetic energy. But if I have that same vehicle and I double its speed, it will have 4 times the speed because the velocity is squared and the mass is only to the first power. So speed is definitely more important than velocity. A bullet has a very small amount of mass, but it's got an incredibly large velocity, giving it a lot of energy. If you've watched the second Terminator movie with Arnold Schwarzenegger, the only way he was able to slow down the other Terminator was by shooting it with a shotgun, because shotgun shell produces a great amount of energy because the pellets will be moving fast and there'll be a lot of them. If you haven't shot a shotgun, you probably don't know what I'm talking about, but it's you need to be super careful and know what you're doing. Get that into your shoulder really tightly, otherwise you could hurt yourself. So if I take this equation, these that are set equal to each other, I rearrange them, and I'm trying to get rid of the square root. I end up with this equation right here. Okay, so this is the speed of gas 1 and the speed of gas 2, and the molar mass of gas 1 and the molar mass of gas 2. Alrighty. So again, this isn't going to tell you the speed of the gases. This is going to tell you the speed relative to another gas. So let's do our argon. So when I do these calculations, our argon and our helium, when I do these calculations, I always make gas number 1 the smaller gas. It just makes things easier. So I'll go rate of helium divided by rate of argon. All right, so that'll be the square root of 40 divided by 4. So make sure you realize that the 2 they swap places. The 2 and the 1 swap places because the speed is inverse to the mass. So they gotta switch sides when they go to the other side. So what's the square root of 10? 30 something. Square root of 10. 3.16. Yay, what does that mean? Well, it's 3.16 divided by 1. Okay, so helium is moving 3.16 times faster than argon. So if the argon is moving 100 miles per hour, then the helium is moving 316 miles per hour. So why would we use this? Well, let's say that there was a chemical spill someplace, and I want to know how fast it takes the gas to move across the countryside. This happened in China, sadly, and a whole bunch of people died because of it. But they did this calculation to determine who they could save and who they couldn't save. And again, people who are creating perfumes are going to be using this calculation to determine just how long that perfume is going to last on the subject. Alrighty, there's Graham's law. And the last thing we have to talk about with this set of notes is called vapor pressure. So vapor pressure is the pressure at which a substance will exhibit at a given temperature. Okay, so what do I mean by that? If you, I mean, it's kind of interesting. Like if you take your keys and you smell them, or you go ahead and grab yourself a pre-82 penny because you know pre-82 pennies are made out of copper. And so we take that penny, let's say you had your eyes closed and somebody was going to put that penny underneath your nose. Are you going to be able to smell it? The answer is yes. And your question would be, well, that's a piece of metal. How am I smelling the metal? The only way you can smell an object is if that object enters your nose and interacts with a nerve. Okay, so how did copper get in my nose? Everything has a vapor pressure, even solids. So you can take your keys and sniff them, and there's definitely metal going up into your nose. Granted, it's very, very little metal, but it definitely will. You can grab a piece of paper. I can smell something on that piece of paper. You can grab the back of my phone here, and I can definitely smell plastic. That means that stuff is coming up into my nose. That means that it has a vapor pressure. So everything has a vapor pressure. And the way we do the vapor pressure is we have something like this. So this is just a closed system, and this is a tube filled with mercury. And I just drop something in here, and then I wait, and I see how much the tube height changes. If this is going to be water, that's fine. We've done this a zillion times. I put liquid water in here, the heights are the same, and then I just wait, and some of the water evaporates. And some of it turns into a liquid, and some of it turns into a gas, some turns back into a liquid. It beats on the surface of this mercury and causes a height differential. And then eventually, the number of particles that are turning into a gas and the number of particles that splash back down in and connect with the water equals, and that's our vapor pressure. It stays at a constant pressure, and then I would measure the height differential and find out. So water would have a certain vapor pressure, but if I put rubbing alcohol in there, the vapor pressure would be much higher. And you know that because rubbing alcohol evaporates very easily. Hand sanitizer evaporates very easily. So you'd have a large vapor pressure with that, mostly because there's a lot of alcohol inside of it. If you put a handful of pennies in there, you probably wouldn't be able to perceive the change in height. But there is a vapor pressure there. If you waited long enough, the penny would just evaporate away in the same way that an ice cube would melt and then evaporate away. Why, side note here, why would we need to be able to smell phenomenally tiny amounts of metal? How could that be useful to us? Well, a long time ago, it was useful to us because if we could smell small, very small quantities of metal in the air, we could smell blood because there's iron in blood. So if you have injured an elk, a deer, moose, good luck with that, a woolly mammoth, more luck with that, and it's running away from you, you can track it down because you literally can smell it. We have kind of lost that, not kind of, we've really pretty much lost that. But if you had a dog with you, that dog wouldn't lose that scent in the same way that a shark is going to smell that metal from a long distance away if there's blood in the water. What they're smelling is the metal from the blood hitting that nerve in their nose, and they're realizing, hey, there's metal there. there's something bleeding, let's go get it. So we're really good at smelling metal because we're going to starve to death if we weren't able to smell blood in the air. And now we don't really need to anymore. So we don't, like if you got some friends that are really, really good hunters, maybe it's because their nose is super keen to that metal smell. And so they can track it a lot better. So whatever's animal is injured. Okay, so what affects vapor pressure? Temperature of the substance. Absolutely. So if we go back up to this and we talk about water, if this water is at room temperature, you're going to get a certain height. But if this water is at, say, 120 degrees Fahrenheit, the height differential is going to be a lot different. And the other thing that changes vapor pressure is the substance. That's it. The water is going to have a certain height differential. Your handful of copper pennies isn't going to have nearly the same height differential. It's going to be a lot less. A squirt of hand sanitizer in there, that's going to have a much greater vapor pressure. And maybe you've experienced this, like using a gas can to put gasoline in a tractor or in a lawnmower. When you open it up, the gas can, there's going to be like a little poof of gas that comes out of there. At least there should be. If not, then you got a bad gas can and you're leaking gas. So if it's a cold day, that puff sound is going to be minimal. Maybe you won't even hear it. But if it's a hot day and the gas can's been sitting in the sun, then you're going to hear a big poof because a whole bunch of that gas has been turned into a vapor inside of that can and then released. Okay, and that is all I've got. That's all the notes we have for the whole class. So thanks for watching.